Well, hello, once again. Greetings from Northern Michigan. It's time for another episode of Flat Earth Can't Science.
I'm your host, Bob the Science Guy, and today we're going to take on one of my favorite flat earth scientists, Phuket Word.
Phuket Word has dozens, if not hundreds, of videos out on the web putting forward his special version of perspective. In fact, he recently put out a 1-hour-long documentary on perspective and navigation in the real world. That video was so special it's probably going to result in several shows of Flat Earth Can't Science, but today we're going to start off with his version of how a sextant works on the flat Earth. So pop some corn, grab a drink, and prepare to be amazed. Lord knows I was. So today's experiment is going to be how to use a sextant on a flat Earth. Okay, so here's what we have. Phuket Word went to Wiki and read about a sextant and how it worked on a spherical Earth. Not to be outdone, he had to figure out some way that it would work on a flat Earth as well. After briefly amazing us with his extensive knowledge of right triangles, he was able to determine a height for the star Polaris. He then continued on to show how we could get sextant readings on a flat Earth, but quickly ran into trouble, which he conveniently got out of by, you guessed it, perspective. Now, the logical fallacy in play here is what's called an argument from ignorance. You see something, you don't know what it is, so then you make up a story as to what you think it is, and then call it good. Examples of this include UFOs. The U, of course, stands for unidentified, and that's the end of the story, but we attribute them to alien civilizations. In the case at hand, Phuket Word clearly has no idea of how to do navigation or use a sextant, but that doesn't stop him. He'll figure out a way to make it work. Well, for those of you unfamiliar with what a sextant is, here's a quick tutorial. Basically, what you're doing is you have a telescope with a semi-glazed mirror in front of you. You line up a star in the sky with the horizon and read off the elevation angle. On the globe, the real world, that angle of declination is your degree of latitude.
Let's go ahead and go over the way a sextant is actually used. Now, if you're standing at the North Pole and you look down at your feet, you can be imagined to be standing on a flat surface. And if you look at the angle from that flat surface directly up to Polaris, you will find that the angle is 90 degrees because it is directly overhead. That is why the North Pole is considered 90 degrees north latitude. Now, if you go down the curve of the Earth about halfway to the equator, and again look down at your feet, you see that you are on a flat plane that is perpendicular to the radius of the Earth right there, a level plane. And you look over to Polaris, you will find that it is 45 degrees above the horizon. Therefore, that is 45 degrees north latitude. Now, if we continue down to the equator, we will see the Polaris is directly on the horizon, or 0 degrees above it. Therefore, the equator is 0 degrees latitude. In order for a sextant to actually work on Earth, two things must occur. The first is that Polaris must be very distant, so distant in fact that the light from Polaris arrives at Earth in parallel lines. The second is that the surface of the Earth has got to be curved. Now, as a surface curves, the angle that is level or perpendicular to the radius at the point of the curve changes. And the angle between that flat level and the light coming in from Polaris is what determines what our latitude is.
Let's let Phuket Word explain this to you in his own words.
This is an instructional video that will explain how to use a sextant observing Polaris to determine your latitude. And of course it assumes a globe Earth model. But in fact, you can also assume a flat Earth and it works perfectly fine in exactly the same way. Okay, so it doesn't matter how high in the sky or how far away Polaris actually is from the North Pole, above the North Pole. What matters is how far away you are from it. So if Polaris is local and you get further and further away, it's going to appear to sink to the horizon, and this will determine your latitudes. The latitude lines on the Earth, flat or round, are determined or were determined by the position of Polaris above the horizon. On the globe model, you assume the Earth's surface is curved. On a flat Earth, you incorporate the reality of perspective. We know that when we have a triangle like this, so we create a triangle with an observation. If we look directly up at something, or this side here of the triangle, the vertical side, can represent the height of a tree or a tower or something above the Earth. And if we have a distance across the flat surface that is equal to this height with this right angle here, we then have an angle here of 45 degrees. So this is when we can use surveying and trigonometry to estimate or calculate the height of something above the surface based on this side, this vertical side, and this horizontal side being the same length and giving us an angle of 45 degrees right here. So it's after that 45 degrees that is important and where perspective kicks in. And again, if he is at the same distance from the tree as the tree is high, we have a right angle here and a line of sight to the observer. Okay, so what we then get is a 90-degree angle here and two 45-degree angles here. And we know then that the distance between the observer and the tree is the same as the height of the tree. So this is the very simple way we can work out the height of something without actually climbing up the tree and physically measuring it with a tape measure. Okay.
You know, I'm sorry, but I'm going to jump back in here for a second. What he has just described is measurements according to parallax. And parallax is precisely how we knew Polaris was 400 light years from Earth. Carry on, Phuket.
But we can see here that the simple fact that something is further away makes it appear much closer to the horizon, or shorter, perspective, angular size, whatever you want to call it. The tree, we know, is physically the same height, so if we wanted to represent it at the same height, we could. But here we are representing what the observer sees.
Okay, I hope you can see the error that he's making right here. When you look at objects down the road, they get smaller as they get further away. If you look at them in the side view, you can't do that. All the objects are represented at exactly the same size. That's the way you actually do an orthotic view with perspective. Now this silly pseudo-perspective is being offered up because of this next diagram. Now on the bottom you can see on a spherical Earth with the light of Polaris coming in parallel rays, you can easily set up an angle matching your latitude. However, you have to adjust the height of Polaris on a flat Earth in order to get the same angles. So by incorrectly decreasing the size of the tree in that side view, he's setting you up to try and sell you on the idea that you can do the same with Polaris to account for the problems with the angles that will arise.
They are using the same methodology as is used for the globe Earth model and applying it to the flat Earth model, for want of a better word. The curve represents perspective. Okay, so they assume that the sight lines should all cross at the position of Polaris, but they don't on flat Earth. Flat Earth model is wrong. No, they're confusing. They're trying to use globe Earth modeling with the flat Earth model. So again, the flat Earth is a model of being on a flat plane, making observations that incorporate the reality of perspective. Whereas the globe Earth takes the reality of perspective and converts it into a curve beneath our feet.
Yep, as you recall, Polaris is some 400 light years away, and when its light arrives at the Earth, it is in parallel rays. That's how I can use a sextant to locate my position on Earth within 100 feet. But I digress. Back to you, Phuket.
This illustration is often used in attempts to debunk the flat Earth, but it's wrong, as it tries to incorporate the modeling method used for the globe into a flat Earth model, but doesn't compensate for perspective, as we saw just now with the trees and the sun. As we get further away from something, it should appear to get closer to the horizon across a flat surface. But here we have all these angles of elevation going to a single point above the flat Earth in this orthographic view, which, okay, may be physically true.
Well, but nothing. It is physically true. This is why a sextant will not work on a flat Earth.
So, in fact, what we do have is a matchup here of 45 degrees latitude and an angle of elevation from the eye level or horizon of the observer to Polaris. 45 degrees at 45 degrees latitude. So we can in fact assume that this may well be correct. The distance from here to here, directly underneath Polaris, would be the same as the height of Polaris above the flat Earth, 4,989 kilometers or 3,100 miles.
Okay, I've had about enough of this, but you heard it here first. Phuket Word has determined the elevation of Polaris to be 3,112 miles above the North Pole. Not 400 light years, 3,112 miles exactly. Well, Phuket, that's really special. Now that I know the height of Polaris above the North Pole, I can actually calculate the angle to Polaris from every degree on the globe from 90 down to the equator. And I've actually done that on a spreadsheet. You can actually download the full spreadsheet. There's a link in the description. In fact, I'd like people to do that just to check my math, because I'm not an astronomer and this isn't my field. There may be some of you out there that are better at it than I am. Now, what I did was I made note of the fact that Phuket says that at 45 degrees north latitude, the angle to Polaris is 45 degrees. That gives me the height of Polaris, and it allows me to calculate the angle to Polaris that the sextant should read on every degree from the North Pole at 90 north all the way down to the equator, and I've put those in the spreadsheet. I can then very easily calculate the difference between the reading on Phuket's special magic pixie dust flat Earth sextant versus the actual location on the Earth and find out how far it is off. As you can see, as I go from the North Pole down to the equator, my error rate just keeps building and building and building, and by the time I get down to the tropics, I'm 1,500 miles from where I thought I was. But wait, there's more. I love listening to him flounder.
The same thing is done with the sun. Again, this is an attempt to debunk flat Earth by showing that the angles from, this time, of course, we have the sun above the equator, and we have angles that do not appear to match up in this orthographic view. Again, not compensating for perspective. So, for example, you get, here they've got the equator over here, over here as well. So yes, the sun should be directly above you at the equator, but the further away you get, so here we're going this direction to get to the North Pole, and by then the sun, if you factor in perspective, will be much, much lower, will appear.
But you know, here's the equator here, and then it goes to the North Pole, and then I guess it's over at the other equator, but it's night there in perspective.
So let's have a look at the kind of results we get when we use this orthographic view and we factor in the reality of the observer's perspective.
Yeah, let's go ahead and do that. Recall that at the North Pole, Polaris is 3,102.3 miles high, according to Phuket Word. So, when you're at the North Pole, it'll be that high. At the equator, we know that we can't see it, so it must be 0. That lets us set up our perspective triangle. Polaris must appear on the top arm of that triangle, going from 0 at the equator to 3,102.2 miles at the North Pole. I went ahead and calculated the angles that Phuket's silly perspective sextant would give me. And I did that for the equator: 15, 30, 45, 60, 75, and 90 degrees. Let's see how far we're off. Well, if we're at the North Pole or the equator, we certainly can find our position. But at my office on the 45th parallel, Trish, my practice manager, is going to be pissed when I call her from the shores of Hudson Bay. Now, I'm sorry, I just have to listen to Phuket Word stumble about for a little longer.
So we have our latitude lines and a vertical line representing where Polaris should be somewhere above here.
Somewhere? You said it was at 3,112.3 miles, Phuket. Somewhere is pretty general. You nailed it to 1/10 of a mile.
We should get something like this. 10, 20, 30, 40, 5 degrees. These are the results that we get when we draw a line that is an angle equal to the latitude. Every 5 degrees of latitude, we get this wonderful curve.
Would somebody that actually passed middle school math explain to Phuket why you get this lovely curve?
We don't have a dome either. Our dome is this curve of perspective, okay? So what we are talking about here for a flat Earth model is a flat surface, and the sun, moon, and stars all in layers that are parallel to the surface. And it's only because of the observations that we make in the sky that create this appearance of a curve or a dome. So when we talk about a dome, it's a dome of perspective. Okay? Yeah? A semi-sphere, if you like. But this sphere, or the dome, is one of perspective. So everything is parallel lines. It's like the flat Earth is like a sandwich. We're in the middle of a sandwich.
A sandwich. We're on a sandwich on a flat Earth. Okay.
I really hope that makes sense. And so there should be no need for anyone to argue that the globe is a fact. The globe is just an abstract mathematical interpretation of the observations that we have made of stars and celestial objects.
And perspective. Don't forget perspective.
Lines of latitude that are drawn and turned into a globe Earth work perfectly fine on the flat Earth when you factor in perspective.
No, Phuket, it really doesn't. It doesn't work with a triangle. It doesn't work with perspective. And quite frankly, this is simply an argument from ignorance. You have no idea what you're talking about, and you're making it up as you go along. Now, normally, when I do a debunk of a flat Earth video, I at least show the flat Earth scientists some respect for an effort. It's like you're not really even trying, and you're just kind of throwing stuff up and seeing whether or not, if you say perspective and horizon rising to eye level and just these buzzwords, that somehow it'll all be okay. Well, it won't, sir. Unfortunately, you sound like a nice guy, but when it comes to science, you're a hack. If you want to change my opinion of you, then let's go ahead and do something that might actually have some merit. You haven't said anything about atmospheric lensing bending the rays of the sextant from Polaris to maybe explain some of this. So why don't you try that? Now, mind you, I didn't say it was going to be easy. If you're going to try and claim that this is atmospheric lensing, you're going to have to account for all of these different refractive indexes, which vary by degree of latitude. And then in order to claim that there must be a lens up there, you don't necessarily have to show me the lens, but you're going to have to show me exactly how you're going to calculate the curve on that lens. Here, let me help you out. There you go. There's the equation to do it. Why don't you go ahead and calculate the lens required to correct the light of Polaris at the equator: 15, 30, 45, 60, 75, and 90 degrees. Should be easy, especially for a super smart guy like you that actually redefined a new field of perspective.
This rabbit hole's too deep for me.